Hey yo, what is up guys? It's your boy. So today we'll be covering transformations. And transformations is a way we actually manipulate graphs, and there's a couple different ways, couple different parameters which affect our transformations. And typically transformations can be expressed with, this one formula or expression. I'll break it down for you. Essentially, when we manipulate a graph, we're manipulating two components. We're manipulating the x component and the y component. And different variables in this expression manipulate different things. So if I broke it down, we call f of x our function, where x is equal to our input. Okay? We call, well, before we jump to that, the outside terms, so essentially A and D affect, actually let me do this in a different color. A and D affect our vertical parameters. Where A is our vertical stretch, and D is our vertical shift / displacements. And so these transform, as the name denotes, these are transformations which affect our y, because it's vertical, right? These affect our y. So in other words, effectively, if we have x, y would be transformed by a factor of a, and the constants of d. Alright? So that's our vertical parameter. Those are our vertical parameters. So our next parameters are our horizontal parameters, which is our b and our c. So this is our horizontal stretch. And then this is our horizontal shift. Okay? And so when we're working with the horizontal parameters, in other words, the parameters that affect our x, you think opposite. And what I mean by that, I'll get into that in a bit. But essentially, when we're working with constants and factors in our horizontal parameters, we actually act by doing the reciprocal. What does that mean? Well, I'll show you. So, let me give you an example. Let me get an example. Say I gave you the function. Let's see. Say I gave you the function f of x is equal to 2f, let's say 3x minus 2 plus d. Let me just see. Yeah, x minus 2 squared plus d. So we're working with a parabolic function. Okay? Well, let's first graph a parabola. So our parabola would look a little bit like this. And And let's graph some critical points. Let's call this 1, 2, 3. Let's call this -1, -2, -3. And let's go by increments of 2, 4, 6, 8, 10. Okay. So typically a parabola has the following x and y coordinates. At x equals 0, we are squaring our function, so we get 0. At x equals 1, we're squaring our function, so we get 1. At x equals 2, we're squaring our function, so we get 4. At x equals 3, we're squaring our function, so we get 9. These are our critical points. And so if we went and essentially did the negative, the same thing would happen. We did -1, we'd still get 1. If we did -2, we'd get 4. -3, we get 9. Why is this? Well, remember, when we square a negative input, we get a positive result. We get a positive result. And so, what we can do is we can now graph this function. Okay, at 0, at x equals 0, we have y equals 0. At x equals 1, we have y equals 1. At x equals 2, we have y equals 4. At x equals 3, we have y equals 9, so right about there. So, at x equals -1, it's just a reflection, it's just a reflection on the, it's a reflection across the y-axis. And so let's connect our points. So yeah, that's a bit about our parent function, which we'll call f of x equals x squared. We call this our parent function. But now let's look at the example. The example is effectively telling us to transform this graph given the parameters in our expression. So before anything, what I like to do is I like to kind of describe my transformations. Remember what we said here is we said that y is multiplied by a multiple of a and is shifted by a constant of d. Okay? And let's actually make d, let's make d, no, I don't know. Let's make d 2. Okay? And so with our x, it's kind of the same principle, but remember earlier I told you that in the bracket's kind of weird. It tells us to think opposite. So let's think opposite. Well, it's kind of like our y. We have a multiple. It's 3. But when we're in the brackets, we always think opposite. So our constant will our multiple will actually be 1/3. And our constants is 2, but remember, think opposite, so it's actually +2. For our y, it's a similar principle. Our a, okay, our a is 2, and our d is 2, right? And so these are the transformations that are effectively reinterpreting our f of x equals x2 parent function graph. So let's do that. Let's use what we plotted out here to determine our new x and y values. So x and y. First one, we have x equals 0, but we transform x equals 0 by our x parameters. So let's do that. Oops. 1/3 0. Oops. No, I don't want you there. 1/3 x 0 plus 2. And for our y, we do the same thing. We do the same thing. 2, 0 plus 2. Okay? And obviously, this just equals 2. This just equals 2. For our 1, we do the same thing. 1/3, 1 plus 2. This equals, I believe this equals 7/3, if I'm not mistaken. And then this is the same thing. So, 2, 1 plus 2 equals 4. Same principle, 1/3, 2 plus 2 equals 2/3. 2/3 plus 6/3 is 8/3. Okay. And then 2 of 2 plus 2 of 2 plus 2 is equal to 4 plus 2, which is 6. Finally, we have 1/3, 3. So some of these just cancel out. Plus 2, that gives us 3. Okay? 2, 3 plus 2 equals 8. So these are effectively our new coordinates. So let's graph our new coordinates. Oh, sorry about the graph. So effectively, we I think I might need a bigger graph. Let me just kinda do this. Okay, so effectively we have a couple of coordinates we want to plot. We have our first coordinate is 2, 2. So let's do that. Let's call this 1, 2, 3, 1, 2, -1, negative, and so on. You get the scale. So let's do 2, 2. 2, 2 is right here. Let's do 7, 1/3, and 4. So 4 is right here. This is 4. And we want 7/3. Well, we're 7/3. 7/3 is about 2. So somewhere here. Okay. And then we have 8/3, 6. And 8/3 is almost 3. And we have 6, which is right here. So somewhere here. And then finally, we have 3 and 8. 3 and 8 is right here. And I will just reflect these, because effectively everything we're doing is a reflection. Something like that. And this is our new parabola. Now notice, the parabola has kind of got skinnier. And why has it got skinnier? Well, because we stretched it by a factor of 2. So our vertical stretch has actually made our graph skinnier. And you can also notice, well, the vertex is now 2 places up, and that's because of our vertical displacement, which placed our vertex 2 units where it should have originally been in the parent function. And then you might also ask, well, it's also shifted 2 places to the right, and that's because we added 2 to the x coordinate. And yeah, that's about it. If you have any other questions, feel free to ask. And yeah, all good.